Welcome to lesson 35. So we're going to talk Z procedures for estimating one proportion. We will gradually work up to 2, but we're going to start with 1. So this is the scenario where there's a population proportion we would like to estimate. So we're going to build a confidence interval to estimate that population proportion. And then we're going to go ahead and follow up with calculating a sample size for desired margin of error. So that's that scenario where they say, hey, we want a 95 or whatever level % confidence interval, and we don't want it any wider than this amount. How big of a sample do we need? So here, confidence interval for P. So this is when we want to estimate the proportion, the population proportion P from a single population. So it is important that we still have a representative sample. Typically, we're going to do this by having a random sample. It is possible to have a representative sample if it's not random. It is harder. So then what changes up here, notice we have 2 conditions here. The second is still a size condition, but if we have binary data, which we do when you have a categorical variable of interest that has 2 categories, you need to ensure that you took a big enough sample that the central limit theorem is going to kick in for the sampling distribution of P hat. So you want to make sure that, and note, this is the first week. The conditions will be different for the confidence interval and different for the hypothesis test. So please be aware of that. It will be a little bit different. So you want to make sure n times P hat is at least 10. What this means is you had at least 10 successes that you observed in your sample, and n times 1 minus P is at least 10. So this means you observed at least 10 failures in your sample. So from there, if you want to calculate your confidence interval, your point estimate is going to be P hat from your sample. We, since are using Z procedures, we get to use Z star again, which means we get to use these values. So that should be a little bit familiar. Times, and then our standard error here is going to be P hat times 1 minus P hat over n, square root all of that. So plug everything in there and you'll have your confidence interval for P. Remember, with proportions don't have units. So when you put your confidence interval together, you shouldn't have units if you're doing a confidence interval for a proportion. So we are going to go ahead, we're going to really run with this coffee cup example. So the manufacturer, they would like to estimate, okay, well, what proportion of all of these cups in this huge batch are defective? They go ahead, they take a random sample of 200 cups from that batch. They find 28 of them are defective. We want to estimate the proportion of all cups that are defective with a 90% confidence interval. So our steps, they're going to stay basically the same. We're going to have our question of interest. We're going to talk about our parameter of interest, take inventory. We're going to look at our conditions, state our confidence level, etc. It's going to be the same steps, really. So for our question of interest, sorry, I did have this typed out a little bit. It's probably better than listening to me awkwardly try to write it out. So what proportion of all coffee cups manufactured in this large batch are defective? So the notation is going to be a little bit different than when we were looking at means. So what proportion? So it's going to be proportion of, and then you're going to put whatever your population is, and then that, and then whatever that variable of interest is. So here, the proportion of all coffee cups manufactured in this batch that are defective. That's what we're looking at. So the notation for how you write a proportion is a little bit different here. My parameter of interest here. So I'm going to use the letter P to represent the population proportion. So it's the proportion of all coffee cups manufactured from this batch that are defective. From there, we're going to go ahead and check our conditions for inference. Did we have a random or representative sample? They take a random sample of 200 cups. I'd say so. And then for here is the sampling distribution of p hat going to be normal based on central limit theorem? So is our sample big enough? So what this comes out to is n times p hat. So 200 times, remember we calculated p hat a few slides ago here, at 0.14. It's just going to get you back to 28 defective cups. And yes, this is greater than or equal to 10, right? That is going to be big enough. If you had 28 defective cups out of 200, you definitely have at least 10 cups that are not defective, right? So 200 times, what, 86%? It's going to be 200 minus 28, so it'd be 172 non-defective cups. Yes, this is going to be at least 10 as well. So things to note for the confidence interval, very specifically for the confidence interval, you can look at the number of successes and the number of failures that you saw in the sample, and from there say, yeah, I saw at least 10 of each, and move on. It will be different for hypothesis tests. It will be a little different. So keep that in mind. But for here, I could say, oh yeah, I saw 28 defective ones, and I saw at least 10 not defective ones, so I'm good. I could have done that. So my confidence level, that's just going to come from the problem, 90%. Since anytime we're doing categorical variable like this, so we're going to use z procedures, which means I can use a z star critical value. So that'd be 1.645. So I don't need to use a t-table. I can just go straight to the z star. So from there, now I want to actually calculate my confidence interval. So this is the setup. It's great if you include this. It's not strictly necessary, but anytime we ask you to show work, what I'm about to write is what we absolutely require here. So here, I observed 14%. This is my point estimate, p hat, plus or minus, my z star was 1.645 times 0.14, 1 minus 0.14 over square root of the over the sample size, all under square root. So I have that there. I can simplify. So anytime we ask you to show us work setup, this is the setup we want. We want to know what numbers you stuck where. That's what we're looking for. The other stuff, so like this step, it's not strictly necessary, but it's useful. Especially if something goes wrong, we can see where it went wrong. And from there, I get something like 0.0996 to 0.1804. So things to know, if I am looking for a confidence interval just for p, it has to be between 0 and 1. Technically, it can be inclusive, but it can't go negative and it can't go above 1, right? If it's 0, it means it never happens. You can't have negative proportions. If it's above 1, it means it happens more often than 100%. And that doesn't make sense either. So if my interval had gone off to either end, I would have wanted to cut it off at 0 or 1, depending on which end it ran off. So here, this template is going to be essential. It's going to pretty much be the same as from the mean, except a couple of the blanks will move around. So for here, the true proportion of, so here we want the population. So all coffee cups manufactured in this batch. So oops, it's a large batch, but I didn't have enough room. Sorry about that. So then the variable of interest, so that are defective, is estimated to be on average between, so this is where I insert my endpoint, so smallest first, 0.0996, and 0.1804, with a point estimate of, so this is just asking for p hat from the sample. So what did I see in the sample? Of 0.14. So to just reiterate here, with 90% confidence, the true proportion of all coffee cups manufactured in this large batch that are defective is estimated to be between 0.0996 and 0.1804, with a point estimate of 0.14. And just a reminder, in general, we're going to usually want at least 2 places past the decimal. For me, most of the time, I'm going to want like 4 if you're doing proportions, just because a lot of times people will switch to percent, and I still want to go 2 places past the decimal. So if I had switched to percent, it would be 9.96% and 18.04%. That kind of idea. So that would be my example here. So from the following information, calculate the 95% confidence interval for P. I think this is a great time to press pause, give this a try, and I will pick it up in a second. Okay, so because I know that my confidence interval is for P, it means that I'm going to use a Z-star critical value, and it's going to be 1.96. X equal 56, this is saying how many successes I have. So this means that P hat is equal to X over N. So 56 out of 93 is going to be my proportion. I recommend putting it in decimal form because most of the time it's not meaningful left as a fraction, people just reading it. So there we go. So there's my point estimate. So if I want to start here, I'm going to have my confidence interval, P hat plus or minus Z star times P hat times 1 minus P hat over N, square root all of that. I'm going to get what? 0.60. Looks like we rounded to 3 places for some reason. I don't know. I'm going to leave it at exact 56/93 plus or minus 1.96 times 56/93 times 37/93 divided by 93. The square root goes over all that before I close my parentheses. And I get something like, I'll get that 0.602 roughly. Obviously they rounded just a little bit. Plus or minus 0.0995. So last time we did Z-methods with a mean, we talked about calculating a sample size. So this is a scenario where the researchers have a specific size confidence interval they have in mind, like, hey, I really want a 90% confidence interval. But they also have a certain width for the interval in mind. Like, oh, I don't want the entire interval to be any wider than this. So remember the margin of error? That's half of the width of your entire interval. So based on that, you can say, hey, I want a 90% confidence interval, but I don't want it any wider than 0.05. You can calculate the minimum sample size. You need to take a sample size of at least this much in order to ensure that you have a 90% confidence interval no wider than 0.05. That kind of idea. The difference we do have, so you'll have the same Z-star. You'll put your margin of error there. Remember, these are proportions. You don't want to put percents at all. It will go sideways. Times P star times 1 minus P star. So what P star is, that's our best guess. So if you have sample information, use p hat. If you have p hat, use p hat. However, if you do not know anything about it, if somebody said, hey, I really want to estimate the proportion of this, and they give you no additional information, the most conservative guess for P star is going to be 0.5. And why that is, it comes down to, if you use P star is equal to 0.5, that maximizes the sample size that's required, the minimum sample size. So you don't want to use 0.5 unless you have to. But if you have no sample information, you can. It's just going to ensure that it's going to be the biggest possible minimum sample size you can have. It's the most conservative guess for our sample size. It ensures that our sample size will be at least big enough. So remember, use p hat if you have it. If you don't have anything, use 1/2. So here, we're still stuck on the coffee cup size. The manufacturer, they want to really estimate the proportion of cups that are defective from this batch. They don't want their margin of error to be any bigger than 0.02, which means they don't want their interval length to be any longer than 0.04. So from endpoint to endpoint, they don't want any longer than 0.04. But my margin of error is 0.02. So if they want to construct a 90% confidence interval, how big of a sample size do we need to take to ensure that it's no wider than this amount? So 90%, so 1.645. And then P star is the last thing that we need to figure out. We do have sample information, so we're going to use that. So P hat, it's going to be equal to 0.14. So that was that 28 out of 200. So here's the setup. I like to focus on this side first and then come back. So my setup here will be my critical value over my margin of error, 0.02 squared, times, so my P star is 0.14, times 1 minus P star, so 1 minus 0.14 is 0.86, is equal to 814.5135. So I'm going to get my sample size is at least 814.5135. So recall, it's one of those things that for sample sizes always round up. So need to sample at least 814 cups. So if you want to estimate the proportion of all cups from this large batch that are defective with a 90% confidence interval that's no wider than 0.04, you're going to need to take a sample of at least 815 cups from this large batch in order to ensure that those properties are met. One way to think about it, you can't sample 814.5 cups, right? You have to sample a whole number. And if you sample 814 cups, it's not quite enough. So you have to round up. Even if I had 814.1, I would have to round up to 815. That's how the sample size rounding works. So that's lesson 35. And we're going to go on to doing a hypothesis test for proportion.